Hello class, my name is Miguel Madruga and today I'm going to be going over ATP Pathways for the CAP 1 assignment for the Kinesiology 516 class at Cal Baptist University. Like I said, we're going to be going over ATP pathways and we're going to look over two particular molecules, glucose and a palmitic fatty acid molecule. And we are going to see how much ATP we could extract from these two molecules. Adenosine triphosphate, as ATP, it is the source of energy used in storage at the cellular level. Um, Adenosine triphosphate is basically adenosine that links with three phosphates. It's also free energy liberated in ATP. Hydrolysis powers all forms of biological work. ATP is often regarded to as the energy currency, of the cells. So we are gonna start off with the glucose molecule. We're just gonna work with one glucose molecule for this PowerPoint. So glucose comes from bigger macro molecules like starches, pastas, carbohydrates, some meats, some type of milks. When it's broken down into like the molecular level, then we get one glucose, and that's where we're entering the cell here today with. So glucose enters the cell into the cytosol, and the first pathway that we're going to look at in the breaking down of ATP would be glycolysis. So in order for this process to start off, we're going to need to give 2 ATP straight away to glycolysis in order just to get it going. But so basically what happens is glucose is a 6-carbon molecule, and through glycolysis it gets broken in half basically into 2 3-carbon molecules that we call pyruvates. In the process of glycolysis, we get a 4 ATP out of that. But remember that we gave 2 away. So total net ATP for glycolysis is 2 ATP. But we also produce this an enzyme, NADH, where it's right now is not important in the glycolysis phase of it, but once we go down the ATP pathway into the electron transport chain, those NADHs get oxidized and become ATP. So they are very important. It's important to keep track of them as we go. So 2 in the glycolysis phase. So once we split that molecule into two 3-carbon molecules, we get pyruvates. And here's where we could talk about a little bit of aerobic versus anaerobic. Anaerobic, it means that oxygen will not be present, and it'll cause the molecule to go into fermentation, and then it'll create lactic acid. Just as a quick example, what that could be is you're exercising and your muscles are not getting enough oxygen. What starts to happen is you get those little pains or those little cramps, and that's lactic acid building up just due to the fact that there is no oxygen present there. On an aerobic level, so we remember we have the 2 3-carbon molecules here that just got split because of glycolysis, and then we are preparing them to go into the Krebs cycle or the citric acid cycle. For that to happen, it has to go through this oxidative decarboxylation, which is a process where basically those carbon 3-carbon molecules, they will lose one of the carbons to form acetylcholine. We need acetylcholine to get into the Krebs cycle. So this process pretty much just gets rid of one of those carbons, makes acetylcholine, and now we are ready to go into the Krebs cycle. So it's also worth mentioning that through oxidative decarboxylation, we get 2 more NADH, 1 per pyruvate that was created up here. So we're acetylcholine now. The total yield for glycolysis was 2 ATP total and 4 NADH, 2 from up here and 2 from down here from this process. So we move on to the citric acid cycle, or as I referred to it a little bit earlier as the Krebs cycle. We have the acetyl-CoA here ready right after glycolysis, ready to go in. What that will do, it's a 2-carbon molecule, will bind with this oxaloacetate, which is a 4-carbon molecule, in order to go through the Krebs cycle, where we'll produce more NADH, NADH, ATP, FADH2, and NADH. So total, you'll get about 3 per cycle. NADHs, 1, 2 FDH, and 1 ATP. But remember, pyruvate was split into 2. So there's 2 acetyl-CoAs that will come in here, bind with oxaloacetate, and go through the cycle to create or produce these yields. So as in the citric acid cycle, uh, we'll get 6 NADHs, 2 ATPs, and 2 FADHs too. So once we get these yields, sorry about that. Once we get these yields, they will get transported to the electron transport chain, where those enzymes pretty much just go through oxidative phosphorylation, and what it basically means is they will lose an electron. They get oxidized, and ATP is produced through that process. This happens in the inner membrane of the mitochondria. So for total yields of from cellular respiration of glucose, we would have glycolysis at 2 ATP, as we mentioned before, because it was total 4 ATP, but minus the 2 that we needed to invest in order to get the process going. We have 2 ATP, 4 NADH, and we times that by 2.5 to get ATP. So we got 10 ATP total from glycolysis. The citric acid will give us 2 ATP, 6 NADHs. Remember, 2 pyruvates. You get 3 NADHs per cycle. Since there's 2 pyruvates, you have to go 2 cycles, so you get 6. And you times that as well also by 2.5, which you get 15 ATP. 2 FADHs, and that is times by 1.5, which you'll get 3 ATP, for a total in one glucose molecule of 32 ATP. Now for the fatty acid catabolism, the palmitate molecule, it is a much bigger molecule. It is a 16-carbon molecule. So we start about here. And instead of going to glycolysis, it goes into beta oxidation. And so what basically happens is that 16-carbon molecule has to be broken down. So it goes through about 7 cycles to break it down in order to get it to our acetyl-CoA that we need to get into the citric acid cycle. So that is basically what is happening here. Is we'll break that down into about 8 acetyl-CoAs. So two two groups of carbon, 2 carbons. So 16 divided by 8, you get your 2 magic number of 2 carbons. So you get about 8 acetyl-CoAs in a beta oxidation, 7 NADHs, and then 7 FADH2s. To keep in mind also here, we are going to need about 2 ATPs just to get this process going. So from here, we have our 8 acetyl-CoAs. We're free to go into the Krebs cycle or citric acid cycle. In the citric acid cycle, as you could remember, oxaloacetate will combine with acetyl-CoA to go through the cycle once again, but this time, much larger number, much larger molecule. It will go 8 times around. And then we will be producing about 24 NADHs, 8 FADH2s, and 8 GTP slash ATPs. So here we have our math that we did, activation and beta oxidation. So we got negative 2 ATP, but then we have 7 ADHs times our magic number of 2.5, we get 17.5 ATP. and 7 FADH2s times 1.5, and we get 10.5 ATP from beta oxidation. The citric cycle, once the acetyl-CoA joins with the oxaloacetate, we get 24 NADHs, 8 FADH2s, and 8 ATP. We times those NADHs times 2.5, and 8 times 1, 8 FADHs times 1.5, and we get our total numbers. So then our total yield from a 1 palmitate fatty acid molecule will be 1.6 ATP. How the pathways interact across exercise and intensity duration. Glucose, it is very good for short-term high intensity exercises. Uh, I used to remember a funny story when I used to play soccer when I was younger. My dad used to just give me one little pack of sugar for a quick burst. What he didn't know, due to the lack of steady and all, is that was just going to cause me to go burn out real quick. So glucose is much faster to produce, but at the same time it also goes away quicker, just because of the size of that molecule and how slow it is and how fast it produces. Fat eventually becomes our main energy source. Don't take me in the wrong way; they do both work at the same time. It's just glucose will come out, will produce quicker. It will also go away quicker. Fat eventually takes over. Um, for quick exercises, 1 to 3 minutes long, you'd want to use glucose because it's quick and you don't need it for too long. For long-term exercises, though, I recommend our body would need that fat energy source to go much longer, not as a high intensity. This goes into the question: why can't we rely on our on on the system that produces the most ATP? And that's simply because fat takes way longer to produce. Glucose is way quicker. So for example, I gave the example here of running after a thief that just stole my wallet. If I was to rely on my fast storage, it would take way too long to get that quick burst, in a fight or flight response. Whereas glucose, it's very quick, and I'd be able to maybe catch a thief or not. I don't know. Primary factors that limit ATP production for glucose and glycolysis, it could be the key glycolytic enzymes, the ones say here, fructose. So the lack of these guys, we wouldn't be able to go through glycolysis. Lack of oxygen, as we went over. The If you're going the oxygen is not present way, you're only gonna get from one glucose molecule about 5% of the energy that you could totally get. So uh, lack or too much oxygen could take a limit on ATD production in that pathway. In the citric acid cycle, oxaloacetate is big because we want the acetyl-CoA to be present there with oxaloacetate, so they form that 6 carbon molecule that it takes to make the citric acid cycle go around. For fatty acids, it would be hormones and how they signal to the body when to activate muscles, when to release fat, and so on. Quick overview is just ATP is our body's source of energy. Glucose yields about 32 ATP, palmitate 106, as we've seen through the math. Both work at the same time. That is very important to understand, is that they will work at the same time. Glucose just burns way quicker, and then our body goes into relying on fat storage. Glucose is awesome for small, quick activities, high intensity, but 1 to 3 minutes long. Whereas fat, you're going to have it for a longer time, but it's going to be low intensity exercise. And lastly, we also went through aerobic versus anaerobic, and how lack of oxygen leads to less ATP produced there. You'll only have about 5% of the energy that you could, whereas in anaerobic, you'll have way more energy. Guys, thank you so much for listening. This is my presentation for week 1.